waiting for Cedric.
The test is 1 hour?
No, more than that.
How long?
Hmm?
How many hours?
It'll go. No, it'll go at least for 2 hours or something. Generally, people take 2 hours, 2.5 hours, whatever time.
Timing will be same.
Oh, so however much time we need then.
2.5 hours generally, yeah.
Okay.
Yeah.
Sure.
All right, maybe. We'll talk about the test at the end of the class. Remind me if I forget, but because I want to get started with the material first. So what I want to do today is the generating function method for the Bessel function, and also give you the integral representation of the Bessel function. That's what I want to do today. So I want to do this, and also integral representation of the Bessel function. All right, this is what.
Have we finished the Bessel function for second time completely?
That is the y, right?
It's the beginning.
That's it.
That's it. I mean, it's a guess. It's a guess, right? I mean, second, yeah, yeah, and which blows up at x equal to 0 in physical situation. It does not. It's a mathematical solution. Does not contribute in general for x equal to, because it becomes infinity. Okay.
We have to remember just the limit form. Right?
Limit form, yeah. It's just some weight factor of j nu and j minus nu x with the cosine nu pi, sine nu pi, whatever it was, yeah. All right. So let's get started with this. Generating function, as you know, is a function of two variables represented by g. And for Bessel function, the generating function is given by this exponential of x over 2 t minus 1 over t, and it produces an infinite series with the coefficient which is nothing but Bessel function, except here n goes from minus infinity to plus infinity. Okay? So the coefficient here So as usual, we get partial of g with respect to x and t and get some identities. But before that, I want to rationalize how anybody would have cooked up this function. I mean, so in this case, it's a bit easier to understand why somebody could have come up with that expression. So let us. I'm just going to give you, basically an argument for it. So this is a, infinite series minus infinity to plus infinity. If you want, you can break this into two parts like this. N greater than 0 plus j of minus n t to the power of minus n. I'm going to include 0 in this, okay? So this includes 0, j0x t to the power of 0 is included. So it's something like this in some sense. So what we independently derived this expression of j in x, we know if it is really Bessel function, I know what it should be, right? I mean, so that also we know from if j and x was indeed the solution of the second order differential equation, then this is given by an expression of this form, which we proved last time. Okay. So if this coefficient, we call it a and x or whatever it is some coefficient, right? And if that coefficient satisfies this property, then that's Bessel function, we know. Okay, that's what I want to prove. Now, how do you think I'm going to prove this? I mean, can you just guess? I mean, something just to. I'm trying to do this in a different way this time. Last time we had all these identities, and then we had to, from there prove it, saying that indeed, basically if you did that way, you have to say x squared this, whatever identity we get, generate from this, would satisfy the following differential equation. That's how last time for Legendre polynomial, we, in the corresponding coefficient, had to satisfy the Legendre differential equation. Here, if you had all the identities, you should be able to prove this. Okay, but I'm just going to, give a shorthand approach in this case. So, what can we do with exponentials if you want to write it in series form? How can I write? Exponential of x over 2 times t is nothing but 1 plus x squared. That is the infinite series, right? And similarly, exponential of minus x over 2t will be nothing but 1 minus x over 2t, t is the denominator in this case, plus 1 over 2 factorial x over okay, so that's infinite series, 1 over 3 factorial this quantity whole cubed. That's the expansion for exponential of x or whatever it is, right? So this I can write as summation of x over some power, let us say s, 1 over s factorial, s going from 0 to infinity, right? S is some integer quantity here. And what about this? If I have to write it in the summation notation, what is this quantity? This second exponential. Basically, I'm writing this as what? Product of this. Right? And I'm trying to see how can I guess this coefficient j and x if my left hand side is that. That's what I'm trying to do. Is changing sign, right? So I should have what? Minus 1 to power something r, let us say, let's call it r, x over 2 to the power of r, t to power of minus r, t is in the denominator, right? So I just took it there, divided by r factorial, r going from 0 to infinity. Right? T is in the denominator to the power of r, but so I took it there. Alright. Alright. So my left hand side then is nothing but I could write it as x over, looks like some series like this. And the infinite series are going from 0 to infinity minus 1 of r, r factorial, x over 2 to the power of r, t to the power of minus r is nothing but all these things. Alright, this is clear? I'm just, because this is I'm breaking this minus infinity to 0 plus 0 to infinity as two different series. That's all I've done. This is 0 to whatever, and this is minus, this has got, other one has got all the negative terms. Okay. Now, I need to get this guy somehow, and this is what I have on the left-hand side. So what do we normally do in such situation? I need to somehow get the coefficient of t to the power of n, yeah, right? So if you compare the coefficient of, sorry, this is t to the power minus n, sorry, right? And you could, yeah, like that, I think. All right, so I need to compare the coefficient of t to the power of n on both sides, then I can get the coefficient t nx. Supposing I just say this is infinite series, I'm looking at the term s equal to, let us say, n plus r. Okay. Then I would have r equal to 0 to infinity. What do I have? R is.
S minus.
I needed s is equal to n minus r, right? I want to look at that term. So minus 1 to, s equal to n minus r, then I would have, I want to cancel that, right? Minus 1 to the power of n, I will have, am I doing it correctly? Let's see. Okay, it leads to x over 2. N minus r, t n minus r, 1 over n minus r factorial. Oh, that is t minus n r. Okay, so I need to cancel that. Sorry, it's t n. I was right previously. Okay, this n plus r factorial. I want to cancel that. I want to have this is. S is then n plus r. Okay, that is t minus r. Okay, good. Okay, and I have r going from 0 to infinity, and minus 1 to the power of r became so 2 s is n plus r. T is n plus r factorial, and I will have, looks like minus 1 to the power of r is it s minus n? I'm looking at one particular term, so I have this. That will get cancelled. R is s minus n, this looks like. Let me just make messing up something it looks like. S is n plus r. R is s minus n in this case, it looks like. Okay. Let's see what's happening.
Basically, you are multiplying and then just writing a summation.
Yeah, I want to get that, I need to get this term, right? I mean, so what I'm trying to do is, somehow have a term which looks like t to the power of n here. So that's why I'm trying to look, one particular term. There are many terms, right, in this.
You're trying to separate t.
I need to get a term from out of this infinite series, one term, and have the power such that it is t to the power of n, right? So that's all I'm trying to do. The way to get is, if this is infinite series, can I have a term s is equal to r plus n? Okay, so that will give me, and that will cancel with this minus r, t to the power of minus r.
Gives t to the power n term.
T to the power of n term, and so wherever it is s, everywhere I'm going to change s to r plus n and compare the coefficient. That's all I'm trying to do, and that should lead to this particular expression.
And for minus n, you will substitute
Similarly,
dharma, yeah.
Yeah, so you can do the same thing, or once you're jnx, you know, you change n to minus n. Okay, I mean, so that's all. It is a very simple step, but I just want to do it correctly. So x over 2 to the power of n plus r. Okay, t is n plus r. Okay, so that way I don't mess up. N plus r factorial. Okay. And then I have this summation, this summation is r going from 0 to infinity. I don't have to do anything there. I have 1 over r factorial, and I'm going to keep minus 1 to the power of r there. X over 2 to the power of r, and this t to the power minus r will cancel with the other one. Okay, so it will become t to the power n. Only in this summation I have to put s equal to r plus n. Okay. One of the terms I'm looking at, and so that is equal to, so then that will have a term, definitely, you know, t to the power of n. So I'm looking at just one, in this infinite series I'm only looking at the coefficient of t to the power of n. Okay, so this will give me t to the power of n, so this will cancel and that, and I'm left with something which now looks like that. Okay, n plus 2r, because there is r here also. So this expression is exactly what I need. Let me explain this a minute. Minus 1 to the power of r going from 0 to infinity of x over 2 n plus 2r. Okay, here is 1r, here is 1r, and so I'm looking at the coefficient of t to the power of n. That's what all I need is that. Okay. Okay, so this is the one term. This has got many terms. I'm looking at just this coefficient t to the power of n. Okay, so then this looks like your this term. Here is s, but r doesn't matter. Okay, so this is nothing but j sub nx. Okay. So so from this exponential, whatever I expand into series, I'm looking at the coefficient of t to the power of n. So that I can evaluate j sub nx. Okay, this has got many powers, right? N equal to j0, j1, j2, but if you want to call it n equal to m or something. So it's an infinite series. I'm looking at a coefficient called n equal to m. Then you call it s equal to r plus m. Okay, that's all I mean. So, and that is nothing but your Bessel function. Okay. So this is way to rationalize why somebody concocted this particular function, because that particular function gives a coefficient which is nothing but your Bessel function. Okay, so here it is easier to look compared to the previous case where we had to, develop several identities and do a lot of algebra. So this because it's a simple function, I'm able to expand that into series, right? And I'm able to do it. That's all it is. Okay. So in order to get what this could be, I have to look at the coefficient of t to the power of n on the other side, and there are several terms, and I'm just picking one particular term. Okay, you can call it n equal to m if this is confusing because it's infinite series. You say I want to look at the term t to the power of m, then that gives you j of mx. Okay, so then you can say s equal to r plus m. So then once I do that, and I'm doing that only for this, okay, because this I'm still keeping this as the full infinite series. In this one, I'm just picking one, and then that gives me how to estimate the coefficient of t to the power of n. That's all it is. Okay, so this is just for you to understand why this function is able to predict, is able to generate a power series with coefficient which is nothing but your Bessel function. So all you have to know is this, expansion for exponential of x, right? I mean, that's all you're using. Okay. Function to series. That's why in this course you have to know all these things. You know, go back and forth between function to infinite series and all that stuff. All right, so let's yeah, I just want to, do some identities and please check whether you're able to prove that x squared, what are the identities I generate, whether you're able to prove that j and x satisfies the Bessel differential equation. I think always fancy those expressions are. Okay, this is useful because if you know J0 and J1, then you can calculate J2. So this is one of the identities. I'll prove that to you. And other one is J of n minus 1 x first derivative of the Bessel function. Okay. Identity 3 is another identity is alright. Okay, this identity will also lead to another expression which is may be needed if you want to really prove that Jn satisfies the Bessel differential equation. Alright. Alright, so to prove this, what should I do? The first one. There are no derivatives there, right? The first one doesn't have derivatives, so I should take partial of g with respect to what? I don't have first derivative of Jn.
Just change the number and add them.
What number?
Then get 2n minus 1.
No, but first decision is, which, that's my generating function.
Okay.
What should I do to get the first expression, right? There are only two things we have been doing to get the identities, right? So you have to take a decision. Should I take partial of g with respect to x or t? That's all I want to know.
So x side.
If you did x, then you will have j prime on the right hand
It's
side.
t. You have to
Exactly.
So I have to do t. So that's the first decision, right?
For
Yeah.
second one,
Yeah. So that's a decision. You got this identity, so which one should I do, right? Instead of wasting your time to do both of them, right? I mean, so because I don't have J prime, if I have J, because we take the partial, right? I
J
mean,
is a function.
yeah, partial of G with respect to two things. I can do X or T, right? I don't want to do X because if I did that, I will end up with J prime, and there's no first derivative of Bessel function in that. Okay, so to get the first identity, I have to do partial of G with respect to T. Alright, so when I do that, what do I get? X over 2, 1 plus 1 over t square, exponential of x over 2, t minus 1 over t, n, j n x, t to the power n minus 1, n going from negative infinity to plus infinity. Alright. So what is this?
This is the same with the
Same as
Yeah.
this infinite series, right? So I can write it as x over 2, 1 plus 1 over t square, summation. I'm going to put it in it if you want, j n x, t to the power n, because that's what that is, right? And n going from minus infinity to plus infinity of n, j sub n x. Space, I'll do that later. Alright, so we have the usual stuff, x over 2, summation n, j sub nx, t to the power n, plus x over 2, summation j sub nx, t to the power n minus 2, summed over n, is nothing but summation n j sub nx, n minus 1, and going from minus infinity to plus infinity. So what should I do? Which power should I compare, and what should I get? We can choose anything. We can always modify that. So should we just go with t to the power n? Okay, on both sides. So that will give me x over 2.
we can go with n minus.
The other one is n, yeah, x over 2 j sub nx, right? Plus that will become n plus 2,
If
right?
we go with n minus, means if we
Yeah,
compare
we
n-
will change n to whatever it is. That's what I mean. It doesn't matter, you know, because I will, to get the identity, I'll just change the n value of n. So all you have to do is compare the same coefficient, and then we will. You could have done it perhaps in one step, right? Okay. So n has to become n plus 1 to compare the coefficient of t to the power n. And but I need this expression, so I'm going to put n going to n minus 1. So that will give you x over 2 j n minus 1 x plus j of n plus 1 x is nothing but n j sub n. So even if you chose the incorrect one, you still can do that. Okay, I mean, so don't worry which one and all. Just stick to one, whatever it is, and then do it. Okay, so okay, so that is that expression. All right. I just have taken the 2n over x to the other side. Okay, so it's exactly the same expression. Okay, Now, should we take partial of g with respect to x now? Because I got prime here. So what do I get? Half t minus 1 over t exponential of x over minus, okay, j prime nx k of n going from negative infinity to plus infinity. Alright, and so this is nothing but my infinite series with Bessel function. Alright, so I can write this as half of t minus 1 over t times summation j sub nx 3 of n going from negative infinity to plus infinity equal to j prime of nx 3 of n going from negative infinity to plus infinity. Alright, so I'm going to take n inside, and we can even make to compare the coefficient of t to the power n or something. We can do that. Compare the coefficient of t to the power n on both sides. Okay, so that will give me the first term. I had to make this has become t to the power n plus 1, so I had to make j of n minus 1 x, right? I mean, that would be the term. Half I've already taken, let us say, to other side, and that is t to the power n minus 1. So I have negative j of n plus 1 x is, okay, that's what I think I have to get. So I just pull inside, right? I mean, so I've done nothing but that expression was j of nx t to the power n plus 1, okay, minus j sub nx of t to the power n minus 1 and going from negative infinity to plus infinity. Okay, there is nothing but 2 times j prime of nx t to the power n summed over n. So, and I'm trying to compare t to the power n, so I have to make n go to n minus 1 and go to n plus 1 in this one. Okay, so that's what we got. Is it clear? Alright. So here I have to, I'm looking at that term, and here I'm looking at n going to n plus 1 term. Alright? To get that relationship. So I'm looking at just at one term of this infinite series, right? I mean, that's all it is. All right. Okay, so so this is what generally, you know, it's a function of 2 variables, so I can just generate 2 identities by taking partial g with respect to x and t. Okay, so that is what we have done. All right, to get this third identity, I'm going to do the following. Okay, this is what I have to do, right? Okay, if you remember, our definition of Bessel function was this is the Bessel function we got when we solved the Bessel differential equation. It's an infinite series, which is this form, right? I need to take, I had to multiply by x nu and then take the derivative. That's what it says, right? I mean, supposing I did that, so x nu times j nu will have, I can introduce something of this nature. So I'm looking at that term, and then I'm going to take the derivative of that. All right. So I have to take d over dx of x nu j nu x. What is that? Minus 1 to the power of p. We are taking the derivative with respect to x, so I just want to separate out the 2 separately so that I don't. So this is 2 nu plus 2p, okay, divided by p factorial, nu plus p factorial. And I have, all of them are constants, right? The only thing that I have to take is derivative of this function. Let me just take it. Minus 1 to the power of p, this is a constant, that's a constant, and that is a constant. Okay. All I have to do is take the derivative of x to the power of 2 nu plus 2p. That's all I have to do. Okay. Which is a simple function, right? I mean, x power, it's like x power n, so I know how to do that. So this is nothing but, this term is nothing but 2 nu plus 2p x or 2 nu plus 2p minus 1. Okay, so this derivative is nothing but that. Okay, so I can write d first derivative of x nu. This is our x nu. J nu x is nothing but I got an extra here, got a 2. Okay, I got, so that 2 is in the numerator, right? This whole thing I'm going to rewrite now as that. It's nothing but 2 times nu plus p x 2 nu plus 2p minus 1. And so I have extra factor of 2, so this will become 2 to the power of nu plus 2p minus 1. And I have got nu plus p here, so this will become nu plus p minus 1 factorial. Okay, right? So I can rewrite the whole thing as follows. Summation minus 1 to the power p, p factorial. This will become nu plus p minus 1 factorial. And then this will become 1 over 2 to the power of nu plus 2p minus 1. Okay. And then I have the x. And then I have that. Okay. So this I can write as what? X of nu plus 2p minus 1. I can separate out so that they are same. So I can write this as what? X of nu times, what's that? Okay, x nu plus 2p minus 1, right? So that way I can again combine that as x over 2 nu plus 2p minus 1, so they have the same factor. And I can pull this out because that's not dependent on the summation. Okay, so whatever I'm left with is nothing but x to the power of nu summation minus 1 to the power of p factorial nu plus p minus 1 factorial x over 2 nu plus 2p minus 1. And what is that? That is your Bessel function, right? I mean, minus 1 to the power p, right? Right? Bessel function of, except nu to the power minus 1. So it's order nu minus 1. So it is j of nu minus 1 x. Because the definition of j nu x is without this, right? I mean, minus 1 to the power p factorial. When nu becomes nu minus 1, all you have to do is you exchange nu to nu minus 1, nu to nu minus 1. So this is nothing but Bessel function of order nu minus 1. So that is nothing but x nu j nu minus x. This is outside. So we have proved that this is nothing but this differential is nothing but x to the power n j of I put a nu is equal to n here, right? I mean, in this case, jn minus 1x. Is this clear what I've done? All we have to do is a simple differential of x to the power something, and that's it. And then I go back and look at the definition, and then here I had, 2 nu. So I separated that, and so it's a fairly simple one, because all I've done is taken the derivative, and x appears only in one term, so it's in the that term x to the power something. So it's a very, very simple differential. I have to, first derivative I have to take. So you can do the same thing, because you know what is j minus nu x. You have to put minus and then take the derivative. So I'm going to leave this as an exercise for you to practice. Okay, I mean, it's exactly the same procedure. What did you say? All right. So I can write, since we have proved this, I can write my left-hand side here as what? X to power. Let me just say. Okay. So since it's derivative of that quantity, my left-hand side is nothing but. Let me just write down this like this. Supposing I now divide this expression by x to the power n minus 1, which is here, then I have x j prime of nx plus n j of nx is nothing but x jn minus 1x. So this identity 3, we call this, becomes something of this nature. And similarly, you can take the derivative of the left-hand side here and divide again by x minus 1. You can generate one more identity, which would be x j prime of n x negative n j sub n x is nothing but minus x j of n plus 1 dx. Alright, so all I've done here is taken the derivative just as I have done there, which will be x to the power minus n j prime of nx minus n x n minus 1, right? Okay. Yeah, and then jnx is nothing but is equal to negative x to the power minus n j of n plus 1x divide by, in this case, x power minus n minus 1, okay? Divide by that, and then that should lead to this particular expression. All right? That corresponds to that, that corresponds to that, okay? So you have these four identities that now you can see, right? You can perhaps take the derivative of this. You will have j double prime nx, and you have to manipulate these, in fact, 1, 2, 3 prime and 4 prime to make sure that it really, the coefficient jn satisfies the Bessel differential equation. Okay, so I'm going to leave that as an exercise, but I just want you to sort of understand. They may become useful in other locations too, but so where these identities came from. Okay, let's now go back to the integral representation of the Bessel function. That's what I want to talk to you, which is an important one. All right. So what we saw was this function, exponential of x over 2 t minus 1 over t, generates this infinite series. Where the coefficient is the Bessel function. Notice it is minus infinity to plus infinity. Okay, you have j. You could have j minus 1x and all that also, right? I mean, j negative half. Here it is integer. We are only talking about integer Bessel functions. All right. So what we do is the following. You can get various representation by substitute for t some function, and I'm going to substitute t as exponential of I theta. Okay, let's if I do that, what do I get? All right. Now what is this quantity? Sin theta plus I sin theta minus, so it is 2i sin theta. So it's I sin theta, right?
Yeah.
So this is nothing but this one. Okay. All right. So you just subtract one from the other. Okay, so that is nothing but 2i sin theta, or that divided by 2 is nothing but I sin theta. So this is nothing but exponential of I of x sin theta is equal to j sin nx, exponential I n theta, and going from negative infinity to plus infinity. All right. Now what is my right hand side here? It's an infinite. It's an infinite series. So let's analyze that. It's interesting actually. so what I have is exponential I x sine theta is, let me separate out maybe J0 term first, okay? N equal to 0, that is the easiest. Then I have J1x exponential of I theta, right? Corresponding n, there's also n equal to minus 1, right? In this infinite series. I also have terms like this. I will have then all the odd terms will be like this, right? I will have a term like this. You get the idea. Then I will have terms like what? J2x exponential of I2 theta, J negative 2x exponential of negative I2 theta, and so on and so forth. Now, what do we know about J minus 1x?
-1.
Minus 1 of,
R and
Yeah.
the same.
yeah. So we learned that J of minus 1x is nothing but negative 1 of n, J sub nx, okay? So that is nothing but negative of J1x, because this term is nothing but negative J1x. What about this? What is J of minus 2x?
It's positive.
Is positive. Okay, so all the,
They will have.
yeah, J minus 1x, let me just write. Minus 1x is negative of J1x. And so all of them, so you can see, this is nothing but
Even
plus J2x, right? Okay, so this is plus J4x. So let me now start writing, and this is negative J3x. So can I combine this then? Okay, can I write it as J0x plus, how do I combine these,
they're the same EI theta.
so I theta negative, yeah. So I
Odd
have,
terms becomes 2i sin theta.
Yeah.
And then
yeah, right. So we have J1 plus, that became negative, right? All the odd terms will have something like this. But even terms are going to be something of this nature. Plus, here it will be plus, right?
yeah.
Alright. So what else can I say? What else can I do now?
Because it combined.
This is cosine theta
Yeah.
plus I sin theta minus cosine theta. So this is becoming what?
I sin theta.
This is
It's
become,
2i
this is, yeah, these terms are becoming 2i
sin theta.
sine theta times j1.
Yeah.
Okay, so all these terms will have 2i multiplied. Okay, 2i. This will be sine 3 theta, j3, and so on and so forth. Okay, so I can now write this in a concise notation, the whole thing, as follows. I can write this as j0x. Okay, I have some terms which are 2i j of 2n minus 1 x sine of 2n minus 1 theta n going from 1 to infinity plus 2 times j2nx, because this will become what the other terms, they'll become what, cosine of 2 theta, right? Cosine theta plus I sin that, so it will be 2 times that. So cosine of 2n theta. Is this clear? All I've done is just combine the even and odd terms, and you will see that you will have n going from 1 to infinity.
You write 2 times J0x.
Huh? What did you say?
You write J0x means 2 times.
Oh, sorry.
So
Yeah.
marking is
Right. So we have this.
That's, yeah.
less marking.
Sorry. Now, so I got real and imaginary terms. So if I compare the real parts to real parts and the imaginary parts to imaginary parts, I'll get two different equations. So let us see what happens. Compare the real parts of right hand side and left hand side. So I have cosine of x sine theta is nothing but J0x plus 2 times n going from 1 to infinity of J2nx cosine of 2n theta. And then this is what Ix sine theta. So imaginary part when you compare, I will have nothing but 2 times j of 2n minus 1 x of sine of 2n minus 1 theta. All right. Is this clear up to this point? All right. So the next step, what I'm going to do is multiply Okay, I'm going to multiply this equation by cosine of m theta, this one by sine of m theta, and integrate between 0 and pi. And let's see what happens, okay?
Cosine of m theta.
Right, yeah. Multiply 1 by cosine of m theta, okay, both sides, and integrate between 0 and pi.
We are integrating this from 0 to pi.
Sorry, pi, yeah, 0 to pi, yeah.
Means why we could just get the range in the minus means 0 to pi. Why we are integrating from 0 to pi is just because the term means great.
I'm going to get an integral representation. So somehow I get j, some expression in integral form. If I do to 0 to pi, what happens to, let's understand what is happening to each one of them, okay? What happens to the first term?
It's possible, it's 0.
M is an integer, sine of m theta over m, upper and that is 0.
0
Okay.
goes to
Okay, so, and what about the second term? What happens to this?
So this is
Looks like cosine A, cosine B. Okay, 2 cosine A, cosine B kind of a thing. Okay,
cos A minus b plus cos.
Yeah.
Cos.
and then
So it's changed to sine, maybe even terms remaining. It's m minus 2n. It's
So if you have, what is cosine, 2 cosine A cosine B is what?
Cos of A plus B plus cos A
Cosine of
A plus B plus cos A minus B.
cosine minus,
I think so.
okay.
This is
Sine.
Can I have it like this?
cos A minus B minus cos A plus B.
Okay, let's keep all these things, okay?
Yeah.
So in our case, what is it? So it is cosine of
A plus B.
m plus 2n.
Yeah, M.
Doesn't matter, m plus 2n. When I integrate over 0 to pi, it's again 0 because
Zero.
integral of sine, you get that term is 0. Then you have cosine of a minus b, which will give me what? That is the term will give me 0 to pi.
Cos
Cosine of m minus
2n
2n
theta.
2n theta
Yeah, that's it.
d theta. Okay. So what happens to this integral? The first part of it will always be 0. I mean,
Yeah.
same argument as that. What about this?
Means it's sine of this if this means for m is equals to 2 and
m equal to 2n only it will contribute, right? I mean, yeah. Otherwise it doesn't
It
contribute.
becomes minus 1 or something.
Yeah. So so if I want to put 2 also here, I mean, okay, doesn't matter. So this is nothing but
Minus sign.
so when it equal to, when m equal to, so we write it in this form, okay?
Yeah, delta.
So it will contribute only this, and at that time it becomes 0.
Yeah.
So it is what? Pi, right?
Yeah.
So this is nothing but pi delta m to n, and I have a 2 also. Is this correct, or I have an extra factor? of 2?
Yeah, because we multiplied by 2 and divide.
Where did I multiply by 2?
No, there is already a 2 there. So we take it inside.
Okay, 2 cosine. So I have
Yeah.
already taken my
Okay,
2
two
inside. So it
inside,
is okay. I've already taken the 2 inside.
Yeah.
Okay. So this is nothing but, so assume this is already taken. Okay. So that is already taken. So this whole integral is nothing but pi times
Delta.
chronicle delta m, comma
For
2n.
even.
Okay. All right. So this is where it is. But if you didn't, if you had something like this, these are orthogonal functions, trigonometric functions. That is nothing but half the range. If you forgot for a minute, there's a 2 here. If you have cosine A, cosine B, it's always half. Whatever the range is, A to B, that range divided by 2 divided by this. Okay, I already taken 2 inside, but I just went from there, right? So
Okay.
so this is nothing but pi Kronecker delta function.
Yeah.
So it contributes only when these 2 arguments are the same. That's all. This means this contributes only when these arguments are the same. Okay, those people who don't know that notation, that's all it does. So this summation then is nothing but what? So
J
because of this, it contributes only when
even number.
m is equal to 2n, right? So this whole thing, let me just summarize in a minute. So if you do this integration, what happens is, that became 0, all right? So this is nothing but, so we had a 2 also somewhere, right? We had a 2 here, right? So that was, I brought it here, and that was pi m comma 2 delta n. So this is nothing but j of pi times j of mx. Okay. This is what you have, where m is even. So that's important at this point, and is equal to 0 otherwise. Okay, when m is odd, it's 0. So I have an expression for jmx, but still I'm not totally happy because it is only true for even m. So have j sub mx is nothing but 1 over pi 0 to pi of cosine of m theta times cosine of x sine theta d theta. Okay. All right. So if I did the same thing for the other expression, I multiply by what? Sine of m theta. I multiply by sine of m theta. Okay. And then integrate between 0 and pi. Okay. Same argument, 2 sine A sine B. This term is going to contribute when cosine of A, when the arguments are the same, right? I mean, so we can write this as, so this becomes nothing but pi times m comma, so this one contributes when m is odd, okay? So I have an expression now for when m is equal to odd. I have another expression for the Bessel function. So this is true for when m is equal to even. I have another expression for the Bessel function when it is odd. So I get this expression now. So because the Dirac delta function, the summation will drop, okay? The summation over n will contribute only when that is equal to, yeah, is equal to 2.
Sine of A plus
Yeah. So, yeah, so we have got these two expressions, right? What did you say?
nothing.
Yeah.
I was thinking to one more item.
Yeah. So, but I want an expression that is true for the entire range, not m equal to odd and all that. So we just add these two expressions because other location is 0. So I can always add and get a single expression for Bessel function that's true for any m, whether it's odd or even. So add these two expressions. So this is the integral representation for Bessel function, true for any m. There is nothing but 1 over pi, 0 to pi of cosine of m theta cosine of x sine theta plus sine of m theta sine of x sine theta. All these things times d theta is equal to 1 over pi. This is like cosine A plus sine A, so it's nothing but 0 to pi of cosine of m minus x sine theta d theta.
Maybe there is 2.
What happened? Oh, this is a
No.
phi. Huh?
No, it's correct.
This is cosine A cosine. Yeah, this is
Yeah.
cosine of A plus B.
A plus B.
Yeah. So let me write down nicely. Okay, 1 over pi. This is just cosine of A minus B kind of a thing, right?
Yeah.
Cosine of m theta minus x sine theta d theta. Okay,
Integral.
integral. Okay, of this whole quantity d theta. Okay, so this expression is true for any n, both odd and even. So this is so-called integral representation of the Bessel function. All right, so let me just touch upon one more thing. So what is J0x, integral representation of J0x?
Is cos x theta.
1 over pi of m equal to 0, right? 0 to pi of cosine of negative x, that doesn't matter, right? So I can write it as,
I think it's 0. No.
so this is what you have, okay? And cosine, because the argument is sine theta, it repeats in all four quadrants. So I can write J0x as 1 over 2 pi of 0 to 2 pi cosine of x sine theta d theta. I can write it like that because the argument here is sine theta here, okay?
So you have 2 comes.
Sorry, pi, yeah.
Yeah.
1 over pi. Now, but we know that since this quantity, on the other hand, 0 to 2 pi of sine of x sine theta d theta is 0. Okay? So what we can, because it's 0, I can add 0 to this, right? I mean, there's no problem about it. Sorry, this is 2 pi, right? I mean, I changed that. So I can add, under term, which is 1 over 2 pi plus 0 to 2 pi of sine of x sine theta d theta. Okay, because that's 0. And if supposing I also multiply by I can also do that. So what generally you see in books, the Bessel function of 0th order, the integral representation, you will see it in this form. This is cosine plus I sine theta, so you would see it in this form, exponential of I x sine theta. So this is what you will see. This expression comes in the Fraunhofer for diffraction through a circular aperture, right? I mean, if you study optics, you will come across this expression. And if you are worrying about where did that come from, I mean, the integral representation, that's where it is, okay? So I just want you to recognize, maybe 611 you come across that, more than, 355 perhaps, I mean, class. So that is the integral representation of the Bessel function of the 0th order, okay? But this is the main expression. So you can, in books you'll find, by substituting, how did we get that? Like, if we, in that expression of the generating function, we just substitute t equal to I theta, okay? That's how we came up with this. There may be other representations you can come up with, okay? So that's all I want to mention. But this is one of the representations. Yeah. All right, we stop here. So let's, any questions about the test that you're going to have? I mean, that you want to clarify for the test number 1? So don't study PDEs at this point. Start just second order differential equations, right? Ordinary power series, Fraunhofer, Wronski method. So those are methods basically. So you have to be very clear about when to use ordinary power series, when to use Fraunhofer. series. So you have to analyze the property of P of x and Q of x. That's how we got. You need to know how to set up the initial root equations. That is important. How to calculate initial root. It's a Frobenius series. You need to know that. So that is what we did, and then we went to Legendre specific, second order differential equation that we come across in physics. So we started with the Bessel differential equation. We looked at the solutions of that.
Bessel is also
part of it. Yeah. So the Legendre polynomial, what did we do? We also learned how to, orthonormal property of that, right? And generating function method for that, and in that we found the generating function is used in electrostatics. To whenever the charge is not at the origin at some place and we calculate potential, we write the distance one over the distance, the magnitude distance in terms of Legendre polynomials, right? So that is the importance of Legendre polynomials in electrostatics, at least. So that was something. It's an important thing because you will see that. And we learned about all the properties of Legendre polynomials, like how to get the P1s, P0x, P1x, and all that. And we said it's easier if you did Rodriguez formula, or the generating function method gives you how to connect different ordered Legendre polynomials. So you learned that, get those identities or use Rodriguez formula. That's also under possibility. Then what did we do? Then we started with Bessel differential equation. Legendre polynomials, the way we solved it was ordinary power series, because we were looking for solution in the range -1 to +1, not the entire range. So we still could, although it has got singularity, but we said in that regime it doesn't have singularity, so we could use ordinary power series. But that's not the case in Bessel differential equation, right? It is a Frobenius series, and so we calculated that the series. So it's a complex one which I wrote, and we learned how to calculate j minus 1x in terms of just looking at the Bessel differential equation, because negative factorials don't exist. The other thing we did was gamma functions, right? Negative factorials can be expressed nicely using gamma functions. So you should know what gamma function is, what's the property of gamma function, right? The recursion relationship, gamma of n plus 1 is n times gamma n, which is the most important one, right? Because from there you can get all this stuff. So that's what it is. So you have to understand the power series method or ordinary power series method. The rest of them are properties. And I would suggest also to learn the derivations of, how to get the orthonormalization property of Legendre polynomials, right? That is important. And how we, once you wrote the generating function, how did we get Pn of x equal to 1 or Pn for x equal to minus 1? Those properties came nicely from the generating function method. And also, if you can look at the Wronskian method, go back and look at the derivation once more, where we got that formula. That's important, right? So everything, about second order differential equation, try to learn the methods. So I'm not looking, I want you to see the steps, basically. Don't miss the steps. That's what I'm looking for, where they're going from one step to the other logically. So that's, I think I've returned the homework so that you can look at it and we'll go through that. So I think between that and homeworks if you have done, I think it should be all right, I think, yeah. If there anything complicated integral coming, I will, try to give you how to, whatever it is, So it will all be self-contained, it's that way, yeah. Okay. Any questions? Homework 4, you had any questions? You had some questions, right? Yeah. I'll go. Yeah. Okay. I will provide the, papers and stuff like that to, you don't have to, I'll just give you so you can write all those papers, blank papers for the test.
No calculators near, right?
You don't need calculator. It's all mathematical. It's just like you don't need anything. No calculator, nothing.
I had a question, kind of very specific, but when we did using the Legendre polynomial to get the 1 over r for electrostatics, how do you know which Legendre polynomial, like do you do L equals 0 or L equals 1, or how do you apply it to those types of problems?
Which one? No, the 1 over r, the distance thing,
Mm-hmm.
that has got the infinite series. Its whole thing, PL, everything is there, right?
Right.
It is not
So it's all of them.
all of them, right?
Yeah.
Yeah, summation over that is there. Yeah, it's everything is there. It's not. I mean, so. Yeah, I mean, we will expand and look at it. L equal to 0, L equal to 1, how it is, right? I mean those terms, but you have everything. The summation is over all else. Actually, it's not. I mean, in quantum mechanics, it'll be like first excited ground state kind of a thing. But here you have all of them is there, and yeah, that's why even the problem that you did, you had summation over S something something.
Right.
P to S, so you have, it had only even